Right, so welcome back to the second session. So I have quite some content, so hopefully I can finish in an hour, but maybe I will take a little bit more time. So just stay with me. Right, so for the second session, continue from the map. So once we have the map, okay, so now we have the map. So the next thing we want to do is to make the robot able to recognize the map or use the map to travel from point A to point B, right? So to travel from point A to point B. So we call it like waypoint navigation. Okay. So, but before we can explain about this autonomous navigation, we need to understand a very important concept about motion planning. So how robot actually do decision making or motion planning. Okay. Uh, I'm going to use sometimes to explain this. So first is like autonomous motion generation. Okay. So for motion planning or path planning, you can see. So let's put in a very simple scenario. Okay, the green box, and then we have location B, which is a point middle. Okay, so imagine this is the environment. Try to explain the concept using this simple model. Okay, and maybe it is not easy to see, but you can see like this whole environment or this whole plane is actually how to say digitalized. I mean, it is actually divided into small boxes. Okay, these are all the boxes, and each box represent one unit of steps. Okay, so the robot will move one step, jump from step one box to another box. Okay, so we try to uh, discretize the whole environment into small boxes, which represent the steps. So how many steps or what is the next step for robot to decide where to move. Okay, so the robot, for example, starting from this green box, which is the original starting position, and this is the goal position. So in every steps, if without obstacle, it will have 8 possible option. Okay, for the next step, which is 2, 4, 6, 8. Yeah, 8. So if you're standing here, you are possible. The next step is either here, 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 or here. Okay, so these are the 8 possible steps for the next step. Okay, so we put this model and we are going to estimate a series of decisions. For example, like if the robot moves to this, then the next one moves to this, then the next one moves to this, until finally reach the goal. Okay, so we are going to do this. So how to do this? So this is a process of doing path planning. Okay, path planning. So we have the whole thing, and over here I explained in a very simple algorithm. For example, the A-star algorithm. So the A-star algorithm, we have many algorithms. In fact, like the whole model and everything that I say here is a very fundamental and basic concept. Okay, in motion planning or robot motion generation, it have a lot of algorithm and ways to do that. So I just show you one of a very basic thing. Okay, so you can explore and read more. If you are interested to read more about A-star algorithm, yeah, go to the web and you can see a lot. Right. So for the A-star algorithm, it is it don't say the shortest distance is because cost not always is the distance. Okay. So but distance can be one of the possible criteria for the cost, right? So for example, like over here, in every step, when I decide the next step, I'm going to calculate for the next step. We calculate like the distance between this point to this point, 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 and so on. And then based on the information I find, I choose the one with give you the smallest value. Okay, so you can see in these boxes we actually have all this value, right? So this value actually represent the cost. And this cost, as I said, it can be distant, okay, and it can be other things. For example, like traveling cost, traveling time, and so on. Okay, it can be anything. So you can define the cost that you want to prioritize and put it here. So every time you calculate all the possibility, what are the costs, and then you put in the value, then you are going to make the decision based on this policy, right? Then what you want is like you are going to find all the possible steps with the possible next step and next step and next step until eventually you found one solution or one path that lead you from your original position or starting position to your goal position. Okay, so that is the concept of using A-star algorithm and motion planning, okay, path planning, right? So I try to put this in another dimension or in another perspective to show you another important concept, which is how to find this path, right? So how to find this path? It is okay. It is actually a search. Sorry, yeah. Okay, it is actually a search problem, right? Search problem, state space, and search problem is actually something a big topic or popular topic in computer science. Okay, but before I explain to you what is state space and what is search problem, let us play a game. Okay, this is something that I always do in my class and make the whole thing very easy to understand. Okay, so this is the Hanoi Tower animation. Okay, so I'm not sure if you heard about Hanoi Tower or not, right? It is actually a game that a lot of robotics application or learning or robot learning, they like to use this example. So for this Hanoi Tower, the rules are very simple. Okay, so we have three pillars, and then you're supposed to move this dish, right, or wheel or dish. Okay, dish. You're supposed to move this dish one by one. Okay, one step by one step. And the only rules is like you cannot put bigger dish on top of smaller dish, which means, for example, like if I move here, then the next step is I have to move here. I cannot put here. Here is not okay. Okay, then this is okay, and this is okay, right? So the rules is like you have to move in such a way that the smaller dish is always on the bigger dish, right? And the challenge is you want to use the least steps or move, okay, in order to transfer all these three uh, from tower 1 to tower 3 in this form. So that is the idea. And this whole thing can be go as complicated as when you add up the dish. Okay, when you add more, then you can see like another figure here is like the minimum. So which means this is actually can be solved mathematically. So the mathematician already solved this thing, and they come up with the equation, and we actually know what are the minimum steps required according based on the number of dish you have, right? So let me show you one simple one. Okay, so for example, like the three dish, this is the most fundamental example. So I'm not sure like which one. Okay, so for example, like I do this. Okay, I think I make a mistake. Yeah, I think I make a mistake. Yeah, I think I make a mistake. Okay, so just to show you like, okay, so I transfer from tower 1 to tower 2, but this is not the correct one, okay? I think I missed the location, which is I supposed to put this thing tower 3 so that I can hit the minimum in order to move this whole thing into the third one. Okay, but I'm not going to waste time. You can find this animation I think on the web, and yeah, you can try this, okay, with the minimum and so on. Okay, so why I want to show you this is like, okay, so now you have the idea about Hanoi Tower. Okay, so for Hanoi Tower, so now I explained the concept of state space and search problem using the Hanoi Tower that I just demonstrated. Right, so for the first time, you have the state number 0, okay, so the state that when you start. So the state is like you have this state. Then on the second steps, right, you can either put this piece, which is you only have two possible steps to go. Okay, I mean two possible options, right, for the as a next step. It's either you put this thing over here or put this thing over here. You don't have any other option. These are the two only option you have. Okay. Then for this one and this one separately, they have another possible next step. For example, like if you put over here, then the possible next step can be either you put this white color one in the middle or you put this thing back. But this one don't make sense because like you are like reversing or you put back into the original state. But it is, although it don't make sense to us because we understand, but sometimes computers they don't understand. So to computer, when you set the rules that possible step, it will give you all the possible steps. So this is still a possible step, right? So we're going to list down and we're going to continue this again and again until finally you reach a branch that lead you to this final result that you want. Okay, so now you can imagine this thing, the Hanoi thing, and you try to relate this to this. So this is the first, this is the 0 state, and then first state, second state, and so on and so on and so on. So can you imagine these two? These two are actually the same, right? Okay. So a few concepts that's important over here is so you have the search tree, which is this, look like tree, and then for each state it is a node, right? Then the connection between the state link. Then you have the start state, which is this one, and the go state, which is this one. Okay, so these are a few things that you want. And then the process of finding this is a search problem. Okay, so now I think you understand all this concept. Okay, let's move forward a bit more faster. Right, so the next thing is, so how to solve, but I try to give you a bigger picture. So we have the search tree in this way, but of course we can write the search tree in this form as well. So the first one, then you have a tree option, then the second one you have a few options and so on. And if you look at this graph, do you think it resembles something like your metro map, right? Your train map and so on. It looks like a metro map, and each of these, for example, is a station, and then in between this station, this is the distance or the cost for the train fare and time and so on. Okay, so you can see instantly you can find application of this thing in real life, okay, which is like a train map. So but this and this is the same. And then now we have another new concept, which is like you need to know what is the n layer and then n child node. So which means how many options possible it can grow and how many layers it need to go down in order to find a solution. Right. So for this search problem is a very interesting topic in computer science, and they use a lot of algorithm to do the search. Okay, you can find a lot. So over here, I show you a very fundamental concept. But if you are interested, you can always find a better one. Okay, you find much more complicated one and can give you a better effect and so on. Right. And just to illustrate you one example, for example, like if you want to know how the computer works, for example, in the chess playing robots like the Deep Blue and so on. So part of the Deep Blue or the chess or everything, they are actually using this algorithm. Okay, and this search problem is solved using calculation. Okay, long ago. This is not something new. This already exists for very long. I mean, many years. It's a search problem in computer science that you can find out. But the recent one, the Go, the AlphaGo, and so on, they are expanding this concept into like machine learning, deep learning, and so on, right? In order to do the search. Okay, but over here I'm showing you a very basic one. Okay, so these are the two, right? So how these two actually solve your problem is that. So because this is a computer science problem, so we are going to use computer to do simple calculation, but over a very big space. Okay, so the first idea to solve or to search the thing is like we are using this what we call the first search, which is we find all the possibility in every step. Okay, so imagine we have one A and then we have two options. Then for B we have another two options. For C we have another two options, and so on. Right. So if we are using this search, we are going to find all the possibility in every layer until we finish finding all the possibility. Then only we go to the next layer. Okay, what concern when we are doing this search is the time and also the space computation. So we have this dimension of algorithm, and this algorithm, it is good in the sense that you will always consider all the possibilities step by step. Okay, so you won't miss any options. You are going to search all the options step by step. But the drawback or the the weakness of this is like it takes a lot of computing power and it is very slow in order for you to find a solution, because you are going to waste a lot of computing power for option that is not going to help you. Why? Is because, like, for example, you try to imagine if your solution is very deep down, maybe like 10, 20, or even 100 layers, then you are going to have very big options for you to, like a lot of options for you to like calculate the possible step for the next thing and so on. Okay, so you try to imagine like if this is like go on 100 steps and you try to imagine how many options it's going to grow. So it is a very slow and it will give. But this is good if, let's say, your solution only needs a few steps, okay, only needs a few iteration, then you can get. Then you are going to be very confident to say that you definitely will find a solution because you are considering every possible option in every steps. Okay, so this is the first search method. Then the second one is the depth first option. So you prioritize the depth rather than the width. Okay, and then you can see the computing space is actually much more smaller compared to the previous one. If you compare this to this one, this value is much smaller than it's much bigger than this value. This is much smaller. Okay, so why this is smaller is because like this time we are going to have some policy to choose one of the option and go down further without finding the one on the same layer. Right, so you can see like from A, then you find B, C, then from B, the second layer, we pick one, and then we go down, and we ignore C first. Then from B, we go to this two, and then we pick another one, and we go down first. So which means we are going down, deep down, rather than we are going sideways. Okay, so it's like this, until we hit a point that we cannot go further. Okay, which is like, for example, if you play the chess, we reach a state that you lost or you cannot go any further. Right, then you will go back one step, and find the next one, and then you go down again. Until you cannot, then you climb up again until, yeah, then you continue this until the end. So that's why the possibility for you to much earlier than the previous one. Okay, but this will give this is good for the search problem that you have very, I mean, like a lot of steps down, but it is not good if how to say, if you have a very short I mean, like if your solution can be found in a few steps, this is not good. It's because like you always go down until the end. Okay, so it depends on whether you can find the solution in smaller layer, then the first one will be better, or if your layer is a lot, then this one might be better. Okay, right. Okay, so the next thing, so how to put this or type this with mobile robots, or what we call the path planning. Okay, so how to combine these two ideas. So in mobile robot, we have our problem like this. So this is your X and Y, and you have your obstacle and your robot, and you're going to move around. So you want to do the path planning like just now. Okay, so what we need to do first is like you're going to convert this into what we call the configuration space, the C space, which is this is very similar to the boxes in the first image, in the first slide that I showed you just now. So we convert to C space, which is you discretize everything into digital, I mean boxes. Then from the boxes, you can start to do your search, right? So instead of searching directly from the visible, which is this one, you convert to C space, which is a representation of robot operation state space. So you convert this into a state space. Okay, maybe you need to read this a few times until you understand, because these two looks the same, but this is actually you after you discretize from this. And because these two are on the same domain, that's why it looks similar. But these two can be in different domain. Okay, especially when we apply this concept to a mobile, a manipulator. So we can do motion planning for manipulator as well, the arm. Okay, and we can do the how to say the path planning and so on with the same concept, but the configuration space is having a different dimension as compared to the mobile robots. Okay, okay, I'm not going to go furthermore. I explained quite a lot on this, so I'm going to go back. So once you understand this, let's hit back to the first one. Okay, this one. So now you understand the concept of search, state space, and so on. So now you understand like, okay, so these are all the possible state, and then the tree like this. So the first one is you have this option, then you first this one, then this, you go to the second layer, which is your option become 1, 2, 3, 4, 5, 6, 7, 8. This 2 is no longer option because it's obstacle. Then you search again and again and again and until here. Then how you want to find this path is either just now you use the depth one or the width one, right? To find all the possibility, and finally you found a path that link you from point A to point B. Okay, so the concept that I just explained to you, you need to like convert into mathematical model and then convert into like coding and put them in practice. But over here, we are not going through that process because we already have the tools in ROS to help you. So the tools to help you is the AMCL. So AMCL help you to do all these things. Although the AMCL that's currently running might not using this algorithm. Why? Is because like I'm telling you a very simple algorithm, and AMCL might use much more complex algorithm. Okay, but I just want to show you the very simple and fundamental concept for this whole thing to work. Right, so now you have an idea how robot is actually doing path planning. Okay, so now we want to combine this idea with the map that we obtained just now. Okay, in order to make the robot able to do path planning and navigate from point A to point B autonomously. All right, okay, so now everything clear. So now let's head to autonomous navigation. Okay, so the things that we use is this AMCL. So AMCL, adaptive Monte Carlo localization. So it's a concept that to find the current location. Then after that, we have other calculation for the path planning. I can't remember for the robot, but you can figure it out. Okay, so they have other things. If you are interested to know more about all this robot navigation and so on, head to ROS navigation. Previously they call it STEP. Okay, but head to ROS navigation package. Over there, you can find all the information you need to understand about how ROS make navigation for robot in general, not just the robot, but robot in general, right? Okay, then next I'm going to show you. So now it's 11:25. Good, I'm on time. So I have another next 20 minutes. I'm going to show you how to implement this in Turtlebot in Gazebo. Okay, so if you want to see the details, you can go to this wiki page to see the detail. But I'm just going to show you the key command. Okay, so I need to do some setup. Okay, so I have this. Okay, and then can I have this slide? Okay, putting over here. So let me run my team viewer. Team viewer background is slightly bigger, so I need it smaller. Still very big. Right. Okay. So I need something smaller. Okay. I think this should be good size. Okay. Right. Right. So the first thing that's similar, we need to use Gazebo environment and social robot instead of real robot. So we run the Gazebo. Oops. Okay. So instead, let me start with okay. Turtlebot Gazebo, and then what is Turtlebot work? Turtlebot work. Okay. So first we run our okay. So we have this very nice everything site. You can see it clearly later on. Okay. Bigger. Oops. Okay. I think this one you can see maybe. Okay. I think this one will look better. Right. Oh, we need this one. Don't know. Okay. That one. Right. Okay. So first is we run the AMCL Turtlebot. You see, first we run the AMCL, and in order to run the AMCL, you need to tell the map that you generated just now. Okay, you are going to tell the map that you generated just now, so that it will use the map data that you just generated. What's wrong with my? Okay, so Turtlebot Gazebo AMCL demo dot launch, and then you're going to do this map file equals to something and something, right? So map file. Oh, okay, it's getting heavier. Map file and something something. Okay, so you're going to type here, right? You are going to type that. Assume that you have done, but since I don't have the map, which is my map is not properly configured, I will use the default map, right? So I'll use the default map, which is I already have it ready before. Okay, so I use the default map, but for you, please use the map that you developed. Okay. Okay, then I need to run the RVs. Okay, so I have the map, and you can see like the autumn receive, everything looks good. Okay, so I'm going to run the third one, which is the RVs, to show you the map. Okay, we need the map in order to do the navigation. So Turtlebot view navigation dot launch. Right. Okay. Okay, this one. Okay. You are going to have your map list, and maybe I need to turn this thing like this so that you can see. Okay, smaller so that you can. Oops, no, I'm not going to move this. I need to move the office. I need to make this more. No, it's a bit hard to make. I need to resize this. Okay, it's because it's very lagging, so it's not easy to control. Okay, good. Right, so you can think a bit. So now it looks okay, right? So now the robot obstacle, and then you have the sensor data, right? Okay, so now you have everything set up, and you want to do the navigation, right? So Ross will do all the calculation. I'm going to show you two ways. So there are two ways actually. Okay, two ways, coding way. So these are the two ways that you can do the. Okay. So the obvious way is you're going to do this, and then which means, for example, I want to ask the robot to come here, click this, then I click on this. See, it starts to generate, and this red line, then the red is the execution. So the robot will try to move and slowly reach there. Okay, I'm not sure why the robot keep on turning over here, but I think it maybe some settings that I didn't put it correctly. But well, it still give you the result that the robot able to navigate nicely until the end position, which is your goal state. Okay, so you give some more time, and the robot is eventually you will reach this point, and this is the one that the point that you want, right? About to do the avoidance and so on. Yeah, and even if you have real object that's moving inside there, the robot is going to do the obstacle avoidance. Okay, but I did that. I don't have time to show it here, but you can try it later on. Okay, with this, you can actually move some furniture to block the robots and so on. Right. Okay, So this is how you to move autonomously. So you want to have your coding, right? So how to do this in coding is that you have something similar. Next thing is you are not going to location. So you need to get the way. In this environment, you want to set a few in front. Maybe this is a, I don't know, it's a rubber here. I'm not sure this is the wall, or maybe you have a door here. Then you can draw this whole thing like a room or a house. Then you have living room, you have kitchen, you have point for the location that you want the robot to travel. Okay, so how to do so? Over here we have a button called publish point. You click in this map. Don't do that, because if you click, it will publish the point. What you need is just, for example, this is the door. So I number. Okay, please take a close look at my cursor. The point actually update. And what? Sorry, X, Y, and Z, not theta. X, Y, and theta. Sorry, X, Y, Z always near to 0. It's because like you're moving in the 2D plane. Okay, so these two values represent the X and Y. Okay, so this or the door that I want. Okay, so I stop my cursor over there, and I run and 1.97 for X and Y. So I record now. So I record now. You can write on the. Then I record another one. For example, this is your cabinet. So okay, cabinet and so on. Or you can do it for kitchen, living room, or right. But this one is just for X and Y. How about do the theta? Because that will be your bonus point or your assignment. Okay, so find out the theta that you want. Okay, it's not easy, so take it as a quiz that you want, right? Okay, but the tips is the theta calculation, your map, building your map, the starting location, and also the direction of your theta. Then based on that reference, you can determine which direction the theta is going to be represented in a quaternion value. Okay, but you need is just the radian from respect to the 0, 0. Okay, so how to determine the theta? I'm just going to show you the X and Y. You go and figure out how the. Okay, I remove this. Okay, doesn't matter. So now I already into your location A in your sample code. So this is the sample code. Let's look at the sample code, how it works. So the sample ROS example over here. So package, you can find your concern is actually the navigation.py. This one. Right, this for your application, but you need to modify this based on how line by line anymore. But what important is this goal position that you want. Okay, the goal position that you want. So value of X and Y over here, and you're figuring out from here. This is in terms of radian. We will do the quaternion transformation and everything. So the logic is for this code, you see, it will start from go to point A. It reach point A, and if the state from reaching point A after original position, why it able to move its own initial position, which is happen here at the initial position, and then you will do once it reach point A, it will the next loop that original position, and that's all. So this is the whole code. Explain to you how it works. So what you're going to do. I select this point and I put the XY here to run this, and then you put this in there. Then this one you got another steps is because you just use this. Okay, 2D pose and it hits like this. Okay, it doesn't matter. So it's not going to do any. Run the code and you set the origin and original position, and this is how you do the navigation. So you can imagine this. Okay. Right, so I guess I come to the is the exercise you can do for this. It's like you're going to combine the speech interaction and also, okay, so you want to design and develop this G mapping things and also the gazebo simulator, right? And you need at least 3 location B and location 3 C. And how are you going to modify that is here. So for example, now you want to develop a robot that you can tell the robot where to go. For example, you want to set, it depends on how you want to set, okay, so the environment. So for example, over here, you want to say that, okay, this kitchen, for example, okay, so you have these 3 points. So like it will tap, for example, when you say robot go to kitchen, then do you want me to go kitchen? Yes, then the robot will send the kitchen with respect to, in the XY to the navigation package, and the robot will move. But of course, initially you need to, right. Then the robot will move to the kitchen. Then you say, okay, robot, please move to the door to find again, living room, and so on. Then after that, you can even like continue that with a face recognition or stuff like that in real world. If let's say you connect this with your camera and so on. Then interaction application. So you can have the navigation run in simulation, and then you can have the speech in real world. So the scenario is like, okay, for example, now we have a guest, ask the robot to ask who is the guest name, for example. Then first, okay, maybe you start from this over there. Then the robot will move from the kitchen to the front door. Then it will interact with the person at the door, record down and hello, how are you and who are you and so on. Then you record down, then you recognize the name and so on. Then you come to tell you like what is the name, and then if you're okay, then you open the door and so on. Yeah. Right, so that is one application that I can just generate based on this. But of course, you can do other things as well, right? So there are many things you can design based on the tools that you have. So again, the same thing. If you want to submit or you want to discuss anything about your code and so on, you can upload to your source code, your map, your design. The design means your map and where is your kitchen, and you draw one, or you draw on your map like where is the kitchen, where is the door, and everything. So your design, and then you have your navigation speech interaction video. So you can do the speech interact, then you record down, then you can record down the RVs to show how the robot move from point A to point B, and then talk to you interactively. Right, so that is a very nice and complete assignment that you can do totally at home. Right, so with that, I come to the end, and for the last 10 minutes, I just want to show you something that this thing, okay, so how actually mobile robots evolve into something big is like, okay, one of the things is like this autonomous vehicle, right, which is over here. I just want to show you this briefly. Not going to run the whole thing. You can see the whole. Okay. We start by understanding where you can see like this is the map. Yeah, so you can see like this, and you can see the simple but concept actually. So I'm going to like, yeah, doing a 3D scan, then we have the 3D image, 3D point cloud and so on. So from a 2D to 3D slam, the slam technique or the concept are still very similar, right? So eventually this can go very far if you're interested in this. But of course, our application and the things that I show you is mainly designed for indoor application, because outdoor, a lot, okay, sorry. Right, so I guess that's all. So I keep like the last 10 minutes for Q&A. Right. Thank you, class. And I'm going to open for question and answer. So if you have anything you want to ask, you can ask me, or else you can put your question in now. I'm going to show you what is the next of this class. So yeah, so you can send me question now. Announcement. Right. Okay. So you look at this online classroom. Track. So I decided to stop this track until just started, and you are totally fine to join the show. Let me do the announcement. So for this online, from the introduction, then slowly, okay, I will do the somewhere, sometimes here. This will be the last one. Yeah, because I hope today we reach the 6th week. So I will put the slides, PDF, and the materials, for example, like visual perception with deep learning and so on. And yeah, the gazebo simulator, how to build the environment, and so on. We actually have a lot more content. I'm not going to do that using this time, okay, because I need to do some explain to you like what would be the changes. So from this point, we will stop this track. Now we will move to the online classroom for the online challenge. You aware about this online challenge? And I actually, and especially since you already follow this track for to do the development. So if you're interested to join, please, yeah, see more information over there. How to join right over here. You can see the video. Okay, but what I want to be like this. Okay, so after you finish like the 6th week, similar to this one. Okay, so we have this open platform online classroom, which is scheduled on Thursday morning. So the same time like this, but it's on Thursday morning, right? So I will encourage you to, if you miss some class or you want to because this class I will do some additional things, and also I will explain the class in the sense that how to prepare the class for the competition. So it is more application based, it is more competition based, and it is more practical. And we have some new tools. For example, like last week introduced a VirtualBox image that help you with all the installation and so on. So some new to attend, and also to bring your teammate or whoever, your friends and whoever, to attend this. So this will be very similar to this class, but with additional content, and also the viewpoint will be more towards preparing for the competition. So if you are interested in the competition, I will encourage you to join this session on Thursday morning, 10 to 12, right? So we start to miss a lot. You don't miss anything actually. So you can come on this Thursday and continue with this class, right? Then for those of you, any of you that will want to know or want to hear this, or you want the class to be in Chinese, okay, so I'm working with our collaborator to run the same track in Chinese language. You can please help me to spread this information for your friends and colleagues and whoever that will prefer the class to be in Chinese as well. So welcome you to join. Okay, then this one maybe not concerned to you. So the one to introduce, like, other than TutorBot, we also have another platform, which is we call it the standard platform, which is using the Pepper Robot. So this time, this online challenge, we actually work with SoftBank Robotics, which is the provider of Pepper Robot, and they actually sponsor us to make enable all the participants without Pepper Robot, without the physical Pepper Robot, to join the competition. So even you don't have Pepper Robot, you still able to join the Pepper Robot competition. Okay, and yeah, I'm open this to you so that you can learn something more. So this content, content that I just delivered to you, or you just know, right, will be very different. So for this standard platform, I will encourage you to join as well. So but for this Pepper Robot, they will have two different tracks, although it's like the 2.5 version is the Python way of development. So the development will use Python. Okay, the choreograph and Python tools is a Python-based development. So the source code, everything is run on Python, right? But on 2.9, everything will run on Android. Okay, okay. So if you want to learn about robot development using Android, I welcome you to come on Thursday night. Okay, you can come and listen and how to actually develop robot using Android. So you will install the Android Studio. You will write code in Java, and even another one called, I'm not sure what is Colin or something. Okay, but the basic is Java. So you are going to write everything in Java and so on. So for those who are interested to learn something new, very new, using Java to and Android to develop robots, with a very cool robot. So Pepper is that give you all the functions and everything. So you are invited. Okay, welcome you to come and join on Thursday night for the 2.9 version, which is the Android version. And if you are interested on the Python version, you can come on Thursday night, which is tonight. Okay, we start tonight the first class for the Chinese version. All these things will be recorded and the material will be put on the web. So even though you can't attend for the time allocated, I mean like schedule here, okay, you can always come back for the information and so on. Right. So I guess that's all for the things that I want to say. So I really thanks all of you for joining this class. I have at least a minimum of 20 for every class, and it's actually reached like 40 plus. Very good turnout for this class. And I don't want to stop interact with you. I hope you can join our other classes and we can continue interact. And if you have any questions, suggestion, I welcome you to discuss in our group, Facebook group. Or you can contact me directly, whether in Facebook or email or anything, okay, any channels that you know. Right. So with that, I would like to say thanks to all of you, and I'm going to close this session. I will stop the recording, and if you have any further question or anything that you want to say, thank you, class, and I will hopefully see you again, right, in any other like